And so I hope you see that that is really the same thing you did in fourth grade. Now, we do need to be a little careful. This brings us back to chapter 1 of this class. Notice that I gave those in feet, so they canceled off. I really need to have the same thing here. So let's do a little bit of units conversion here. And so as I said back in chapter 1, it is not cm for centimeter, it's c for centa, and then m for meter. So let me replace centa with what it means, 10 to the minus 2. Oh, let me put the meter here. And so you can see the meter will cancel off. The number 2 I'll just leave alone. And then, of course, if you remember a little bit of your exponents, you could bring this up and change the sign. So this would be 10 to the minus 2, and then plus 10. And so that makes 2 times 10 to the 8th. And I suppose if you wanted to write it out, that would be 200 million. And so, again, not really knowing much more than the roughly size of this box, I could tell you how many atoms are in the face, because the size of the aluminum ones are 10 to the minus 10, and the box is just 2 centimeters wide. So this would tell me that 200 million atoms fit across in that first row. And then, of course, let's do this. How many atoms would fit down in a column? Well, I hope you're seeing it's the same thing. It would be the 200 million, right? It's the same atoms. It's the same 2 centimeters. And so I would get 200 million this way also. So to finally answer this question, how many would fit on this face, I would say it would be 200 million multiplied by 200 million. And I will write the 200 million as times 10 to the 8th. So 2 times 2 is 4. And 10 to the 8th times 10 to the 8th is 10 to the 16th. And so there's my answer. 4 times 10 to the 16th is a rough answer. Like I said, it's not perfect, because this is not the exact size of the atom, but it's pretty close. And so what we call order of magnitude, I just forget the 4, there's about 10 to the 16th. And so what would that look like? I guess I'd have a 4. And then I'm supposed to have 16 zeros. So 1, 2, 3, 1, 2, 3, 1, 2, 3. And one more, is that right? 3, 6, 9, 12, oh, one more. 3, 6, 9, 12, 15, 16. Oh, and I don't even know if I can say that number. What is this? Thousands, millions, billions, trillions, quadrillions. Yeah, so there's 40 quadrillion atoms, aluminum atoms on this face. Which, by the way, we start to get to big numbers. Many times it's better to do this. Write it in groups of 9, and then this would be, let's see, let me go, if at 9, that'd be 7 more. Let me do a 6, and then a 10. All right. So it's become common practice, instead of saying 40 quadrillion, is to group things in billions and millions. So this would be 40 million billion atoms on the surface. And so that's how many atoms I have. Now, let me switch blocks here for a second. Let me come over to this one, which, remember, this is lead. How many atoms are on the face of this block of lead? Now, let me point out that the block of lead is also 2 centimeters by 2 centimeters. Let me point out that lead is almost the same size. Exactly? No, not exactly. Like I said, are all adult humans the same size? No. But I could roughly say that a human adult is about 2 meters. Now, well, 2 meters is a little bit high, because that would be, about 6'8". So most humans are a little bit less than 2 meters. But they're definitely not 3 meters, and they're definitely not 1 meter. They're definitely not 10 meters, and so a rough number would be, I just use 2 meters for the size of a human. So if I just roughly wanted to know how many humans could I stack to get to the top of the atmosphere, I'd just take, well, what's the height to the top of the atmosphere, and divide by 2 meters. That's roughly what a human is. And that's what I'm saying here. I'm taking this and figuring out what it is on a rough idea of the size of an atom. And here's the neat thing about it, though, is it doesn't matter that it's lead. It's the same number. Lead is about the same size. And so if you have the same face for lead as you do for aluminum, for any of them, I could have gold or silver or nickel or tin or copper or cobalt. It doesn't matter. I could pick any of those. And the answer is, how many atoms would I have on the surface would still come out to be 40 quadrillion. 4 times 10 to the 16. And so that's what's neat about this. I'll call it maybe a little overly generalized, but in rough numbers, that is the size of the atom. And so that allows us to figure out how many. And you have a couple of homework problems like that. They say, how many atoms fit on the face of this piece of metal? Or they say, how many atoms... maybe they do 3 dimension. How many atoms are in the whole block? And so in 3 dimensions, hopefully you would see that I would have to go 200 million by 200 million by 200 million. And so I would multiply 200 million together 3 times to figure out how many atoms are in the whole cube of those. Well, let's keep talking, because here's another question. What is the mass of the atom? Now, sadly, my analogy of humans kind of falls apart here, because the mass changes significantly from the smallest one to the biggest one. We cannot just say approximately. Where humans, well, I don't know if I want to go down that road. Humans don't vary nearly as much as the atoms do. I mean, let's look at some of these numbers on the periodic table. Remember I said that the nucleon number is also its atomic mass. And so if we just look at this lower right-hand corner, that has a number of 1. And if we go all the way to the biggest natural one, it is 238. This one is 238 times bigger, not size-wise bigger, mass-wise bigger than the smallest one. That is not even close to being roughly the same. So sadly, we don't have quite as an easy option when we talk about the mass of the atoms as we do the size. The size, we can just kind of ballpark it. But this would be like saying, if the smallest adult was about 100 pounds, then the biggest adult would be over 200 times that. That would be, 20,000 pounds. And humans, adults don't vary that much. But atoms do. Atoms vary by a lot. So, one thing that I'm trying to point out that can easily throw you off is, even though we can do a generalization here about any atom, we cannot with the mass. When it comes to the mass, you have to say, okay, what atom are you talking about? And that's why they're listed on this periodic table. If you'll notice on this periodic table, it doesn't tell you their size. And the reason it doesn't tell you their size is because everybody knows the size. The size of them is about universal for all of them. There's no point in putting it in that table. Everybody knows what it is. I can look at gold or silver or aluminum and I know its size. But I can't do that for its mass. And everyone is very different, and so it's got to be listed on this table. And so that's why we have the mass listed on this table, but we do not have the size. Be careful with that, because I have seen over and over throughout the years students who sit down to do the homework or do down the second test, and it says something about how many atoms are on the surface, and they don't even tell you what kind of atoms they are. They do not tell you whether they are aluminum or they're gold or they're silver. And like I'm trying to point out here, if they're asking you based upon size, that doesn't matter. That's why they won't tell you what kind. They'll just say how many atoms. And many times I get questions from students during the exam, and they go, well, it just says atoms, but what kind? Are we talking about aluminum ones? And I'm trying to answer that now. It won't matter. However, there are other questions that ask for how many atoms, and they base it on its mass. And in that case, since the mass changes significantly from atom to atom, they got to tell you which do you have. And so they might say something like this: I have 90 grams of aluminum here. How many atoms is that? Or I have 400 grams of lead. How many atoms is that? And so if you're ever asked to calculate how many atoms based upon mass, you need the periodic table. You need to look up what the mass of those individual ones are. But if you're ever asked to calculate how many atoms based upon size, they don't need to tell you what kind they are. You don't even need the periodic table. And that's what I'm trying to point out here. All right, so let's have a further discussion about these, what I called nucleon numbers. But as you might be a little bit more familiar with, and it's even labeled at the most common name, it's atomic weight, which they have the bromine here, and they list the 79.9. Why don't I start a little simpler? Why don't I go to the hydrogen, and the hydrogen says 1.008. Now, as I said, if we think of that as its nucleon number, that would tell me that most of the hydrogen has one nucleon, which is the one proton, but a few of them must have either one or two neutrons to make the number of nucleons a little bit higher than one on average. But we already did that. That's nucleons. Let's look at that number in terms of mass. Because as I was saying here, each proton, and so let me just put a P with a plus for a proton, or each neutron, let me just put N for neutron, has a mass that is about what we call 1 atomic mass unit. They roughly weigh the same. Now, an atomic mass unit is about 1.66 times 10 to the negative 27 kilograms. And so times 10 to the negative 27 is a real small number. So not a surprise that the mass of one proton or one neutron is really, really small in terms of kilograms. So an atomic mass unit, an AMU, is a way of taking these small numbers and maybe having them look not so small. But when I see on that chart 1.008, that tells me that on average, the mass of one hydrogen is 1.008 atomic mass units. Remember the helium we did a little while ago? Helium. The number up there was 4.003. And what that would mean is if I had one atom of helium, its mass on average, okay, and it's important I say on average, because the truth is it either has a 4 or a 5. It's not really ever 4.003. But on average, it's 4.003. So if I had a whole container on them and I want to know what is the mass of an individual one on average, it would be 4.003 atomic mass units. And of course, let me take this back to chapter 1. Let's do a unit conversion. You were, of course, converting the easy stuff back in chapter 1. But I hope you see this is the same thing. If I wanted to know what this mass was in kilograms, I could then just replace what an atomic mass unit is. So let's try that. 1.008 is this number. And as I've said throughout the semester here, to convert units, treat your units just like you would a number. And you saw me do that a moment ago with centimeters. I just put the centa as a number, 10 to the minus 2. And I'm going to do that again here. I'm going to treat something that is probably new to most of you, this atomic mass unit, and I'm just going to do the unit conversion. And so in place of an atomic mass unit, in place of an AMU, I'm going to put its value. It would be like in a math class, if you had 5x equals, and that's the problem, and then they tell you x is equal to 3, you, of course, then would replace the x with what it means. It means 3. So I'm replacing the unit, atomic mass unit, with what it means. It means 1.66 times 10 to the minus 27 kilograms. Now, I'll need a calculator here for this. So grabbing my calculator and going 1.008 times 1.66 times 10 to the negative 27, I get a mass of 1.67 times 10 to the negative 27 kilograms. So if I wanted to know the mass of hydrogen in terms of the units that I'm familiar with, which is kilograms, that's what I would do. But I think you will find out as we continue that atomic mass units is a nice unit of unit, so you'll get comfortable with that. Same thing here. I would go 4.003, and then to do my unit conversion, 1.6 times 10 to the negative 27 kilograms. And so grabbing my calculator here, 4.003 times 1.66 times 10 to the negative 27, I come up with 6.64 times 10 to the negative 27 kilograms. And it looks like we better wrap it up here for today. But let me do one more big one to show you how these can change dramatically. Let's go all the way down to uranium. Now uranium, and let me point it out again. To figure out its mass, I got to come to the periodic table. When it comes to size, I don't have to do that. I know the size of all these. It's not listed anywhere in here. I know it. I told it to you. They're all the same. But when it comes to mass, I got to come over here to the periodic table. And so this number right down here is telling me how much mass does one atom have. And I'll just go to 238. I won't do the fraction. And so 238. And so uranium, big capital U, is 238 atomic mass units. And if I convert that into kilograms, that would be 238 times 1.66 times 10 to the negative 27 kilograms. Getting my calculator, 238 times 1.66 times 10 to the negative 27, coming up to be 3.95 times 10 to the negative 25. And I'll even change colors and highlight it here. Here's the point I'm trying to make. The difference in the mass, this is 10 times bigger than that one. A different number of zeros. Two zeros different. That's a factor of 100. And so this is huge. And that's why we can't just say, oh, yeah, they're all the same mass. No, they're not. Not even close. So we list that in the periodic table. But size, we don't. It's not in the periodic table. We know what it is. So watch those questions when they ask you how many atoms do you have. Now it's too bad I ran out of time for today, but we'll pick this up tomorrow, because I might really, this is what I really want to ask you next. Because how many atoms then would be in this whole block if I know its mass? But I'll do that tomorrow. It's time to stop the lecture here for today and then head on over to the lab. So more on the structure of matter, and we will continue this. Oh, and this is the end of the week. So I said tomorrow, but I guess I really mean next Monday. So we'll continue this discussion next Monday. Bye now.